objection, the chair is authorized to declare recess at any time. We're delighted to see everyone this morning, and welcome to our witnesses. I'm eager to hear more about this exciting breakthrough. Not long ago, scientists were not sure black holes were real. Even Einstein had his doubts. Scientists have since uncovered evidence of black holes, but they had no way to capture an image until the Event Horizon Telescope. In science, most knowledge is gained incrementally from efforts to peer into the far reaches of the universe. The experiments conducted at the smallest scale, our collective understanding of the world around us is built piece by piece. Each hard-earned discovery brings reality into a better focus. Every once in a while, a discovery will jolt us forward. Such breakthroughs generate entirely new avenues and tools for scientific study and a new appreciation for what we can achieve. The black hole image captured by the Event Horizon Telescope is both a jolt and the culmination of decades of incremental advances, most of which were made possible by the National Science Foundation. The dark shadow bounded by a ring of light may look simple enough, but don't be fooled. The first ever image of a black hole is a groundbreaking advancement in science, setting the stage for a new era of black hole astronomy. This new Earth-sized telescope also opens up a new window for observation of other astronomical objects and may further our understanding of gravity and the evolution of galaxies. An enormous amount of effort went into clearing the necessary technological, logistical, political, and scientific hurdles. While there was never a guarantee that this project would succeed, the National Science Foundation invested in a good idea with potentially enormous payoff. This achievement demonstrates that when the federal government invests in our nation's best and brightest and the facilities necessary to do cutting-edge science, and importantly, remains committed to those investments, we are limited only by our imaginations. I congratulate each of our witnesses and the entire Event Horizon Telescope team on this astonishing achievement. Another important of this story is the international partnership. This discovery would not have been possible without contributions from partners around the world, including from Spain, Chile, Mexico, Europe, Taiwan, China, South Korea, and Japan. At a time of rising global tensions, let this be a reminder that the pursuit of science is still a unifying force. Perhaps the most lasting impact of this discovery will be the inspiration for students to pursue STEM studies. The excitement of this discovery has no doubt instilled a hunger that will drive the next generation of scientists to make discoveries of their own. Today, we celebrate your success. I look forward to learning more about this incredible image, the global team that made it possible, and future plans for the Event Horizon Telescope. I now will recognize Mr. Lucas for his statement.
Thank you, Chairwoman Johnson, for holding this hearing, and thank you all to all of our witnesses for coming to discuss this incredible discovery. Since Einstein predicted the existence of black holes, scientists have been able to observe their effects and refine theories on how they affect our universe. But this is the first time we've been able to see a black hole directly, and it marks a huge milestone in our understanding of the universe. We have this first ever image of a black hole thanks to pioneering collaboration between observatories around the world. To detect an image of a black hole, we needed a telescope as big as our entire planet. Not surprisingly, building that was out of the question. But every challenge presents an opportunity, and science Science funded by the National Science Foundation joined forces with astronomers, data scientists around the world to coordinate their observations, in effect creating a global telescope. This is a great example of NSF's approach to basic research in driving scientific progress. And as Dr. Córdova told this committee just last week, NSF's 10 big ideas are about enabling research that crosses scientific disciplines to make big discoveries. NSF's coordinated and interdisciplinary approach has already produced 2 groundbreaking discoveries in its window on the universe. First, the detection of gravitational waves by LIGO, and now this image of a black hole. I want to put these achievements in perspective. When Einstein predicted the existence of gravitational waves, he also questioned whether these ripples in space-time could ever be observed on Earth. The signals are so small, traveling over such an enormous distance, that he doubted whether we would ever be able to create instruments sensitive enough to detect them. But now, 100 years later, technology funded by the NSF, developed over decades, makes it possible for us to confirm this fundamental prediction. That matters not only because it helps us understand the universe in which we live, it also because it contributed to the creation of other technologies that directly affect scientific progress, including semiconductors that our cell phones and computers use more powerful. The NSF's investments in ground-based astronomy have also given birth to technologies used in everything from airport security to LASIK eye surgery. But the scientists these projects have produced may be the greatest return on our investment. Hundreds of graduate students worked on this discovery, and their careers will be informed by this experience. And thousands of young students who watch this announcement may be inspired to pursue careers in STEM. These are whole generations of new discoveries that will contribute to scientific knowledge and American progress. We don't know yet all the ways in which the Event Horizon Telescope will broaden our knowledge of the universe or our technological development here on Earth, but it's certain this image is just the beginning of what's to come. I'm looking forward to learning more about this from our witnesses, what their discoveries teach us about the universe, what lessons we can take away from how to coordinate basic research in the U.S., and what's next for this project. Thank you for being here, and I yield back the balance of my time, Chair.
Thank you, Mr. Lucas. If there are members who wish to submit additional opening statements, your statements will be added to the record at this point. And at this time, I'll introduce our witnesses. Our first witness will be Dr. Franz Córdova. Dr. Córdova was confirmed as the 14th director of the National Science Foundation in 2014. She's president emeritus of Purdue University. I think we might have some people here on this committee who might be a little biased for Purdue. And chancellor emeritus of the University of California at Riverside. Previously, she was chief scientist at the National Aeronautics and Space Administration. Dr. Córdova also headed the Department of Astronomy and Astrophysics at Pennsylvania State University and was a deputy group leader in Earth and Space Sciences at the Los Alamos National Laboratory. She received her Bachelor of Arts from Stanford, a doctorate in physics from California Institute of Technology. And our next witness is Dr. Shepard Doeleman. Dr. Mo Doeleman is director of Event Horizon Telescope and an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. He's also a Harvard Senior Research Fellow and project co-leader of the Harvard Black Hole Initiative. He received his Bachelor of Arts degree from Reed College and his PhD in astrophysics from MIT. Our third witness is Dr. Colin Lonsdale. Dr. Lonsdale is the director of the MIT Haystack Observatory, where he has worked as a radio astronomer for 32 years. He has been heavily involved in development of new techniques and instruments in radio astronomy, including the VLBI. He has been involved in the EHT project since it started. He also serves on the governing board of the International EHT Collaboration as vice chair and member of the board of the executive group. He received his Bachelor of Science from St. Andrews University in Scotland and his PhD in radio astronomy from Nuffield Radio Astronomy Labs in England. Our final witness is Dr. Katherine Bouman. Dr. Bowman is currently a postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics. In June 2019, she will be starting as an assistant professor in the Computing and Mathematical Sciences Department at the California Institute of Technology. As a member of the EHT collaboration, she worked to develop innovative ways to combine techniques from astronomy and computer science to construct the first image of a black hole. She received her BSE from the University of Michigan and her PhD from MIT. Our witnesses should know that we will allow each of you 5 minutes for the spoken testimony. Your written testimony will be included in the record for the hearing. When all of you have completed your spoken testimony, we will begin questions, and each member will have 5 minutes to question the panel. We'll start with Dr. Córdova.
Chairwoman Johnson, Ranking Member Lucas, and members of the committee, thank you for holding this hearing and for the opportunity to discuss the Event Horizon Telescope, or EHT, collaboration and the resulting first image of a supermassive black hole, and thank you for your commitment to science. We're excited by this remarkable accomplishment, one that will transform and enhance our understanding of black holes. And I'd like to pause for a minute so that we can all in this room recognize the representatives of the EHT team. I want to focus my remarks today on EHT's history with the National Science Foundation, the vision and support of so many dedicated researchers, and what this discovery means for the future of scientific research. Black holes have captivated the imaginations of scientists and the public for decades. No single telescope on Earth has the sharpness to create an image of a black hole. This team did what all good researchers do. They innovated. The EHT observations synchronized telescope facilities around the world to form one huge Earth-sized telescope. While this technique, called Very Long Baseline Interferometry, or VLBI, was initially supported by NSF in the late 1960s, the EHT team took it to a whole new level. They developed the extraordinary sharpness and sensitivity required to image a black hole. Enabled by technology, observations have always advanced our understanding of the universe, and that is why, for more than 30 years, NSF has supported technology development for astronomy through the Advanced Technologies and Instrumentation Program. This program supported EHT with 8 separate awards that got the project started and sustained its early development. Without this early seed funding, the EHT would not have succeeded. Thanks to its early support, the EHT project grew from a small exploratory group to a large international collaboration. This discovery would not have been possible without cooperation and coordination. Such cooperation is exemplified in the telescope in Chile called ALMA, which was crucial to EHT's success. While ALMA is a major NSF-supported facility, it's also supported by international partners. The success of the EHT also highlights the need for mid-scale research infrastructure, one of NSF's 10 big ideas. After more than a decade of development and piecemeal funding, the EHT was finally reviewed as a whole in our Division of Astronomical Sciences mid-scale program, where EHT received the funding that enabled these observations. Increased NSF support of mid-scale research will enable more effective support of comparably sized projects in the future. Supporting basic research has tremendous benefits. As an example, the methods developed by astronomers in the late 1960s for measuring positions of distant galaxies had surprising down-to-earth benefits. These galaxies served as a reference for measuring imperceptible changes in the orientation and rotation of the Earth. Such measurements are now used routinely to aid modern satellite navigation and the Global Positioning System, GPS. Everyone who uses a smartphone to find directions or search for a nearby restaurant or reserve a ride share benefits from astronomy and decades of federal investment in such basic research. In producing the first image of a black hole, the EHT has generated a global phenomenon. Astronomy is a point of entry for young people into STEM. This is incredibly important to our nation's competitiveness and economic success, as science and technology are drivers of the economy. Our future prosperity depends on inspiring the next generation to be curious, to learn and explore. And I'm happy to see lots of next generation scientists and engineers in the audience today. Astronomy is a source of such inspiration. It's just as important that we continue to support the students and postdocs as they enter their chosen fields. Their contributions were key to this success, and this experience will prepare them to reach even further in the future. This discovery is historic for astrophysics. It's incredibly meaningful for me personally as an astrophysicist. NSF exists to enable scientists and engineers to illuminate the unknown, to reveal the subtle and complex majesty of our universe. Thank you again for your continued support for NSF's mission and for holding this hearing today and the opportunity to testify.
Thank you very much. Who's our next one?
No, Dr. Doeleman. Recognize Dr. Doeleman.
Dr. Doeleman.
Chairwoman Johnson, Ranking Member Lucas, members of the committee, thank you for the opportunity today to describe the recent EHT results and their impact. On April 10th, 2019, our collaboration held simultaneous international press conferences to announce the first image of a black hole. And as you see, if you did see this image, you were not alone. On the front page of almost every major newspaper in the world, you could see the bright ring caused by light bending and the immense gravity of a supermassive black hole that is 6.5 billion times the mass of our sun. It's estimated that 4.5 billion people saw these results, all eyes focused on the same cosmic wonder at the same time. Why did this result resonate with so many people, scientists and the curious public alike? In part, it was because for over 100 years, black holes have remained one of the greatest mysteries of modern physics. They are gravity run amok, a complete collapse of matter into a volume so small that nothing, not even light, can escape their gravitational pull. And based on growing evidence, we now believe that supermassive black holes, with masses of millions or billions of times our suns, exist in the centers of all galaxies. There, the hot gas that surrounds them can outshine the combined light of all the stars in their host galaxy. This animation shows how light rays from this hot gas are bent by the black hole, shown here outlined in red. Some light paths make complete loops around the black hole, forming a bright circular boundary around the event horizon, the point where gravity traps the light, preventing it from reaching us. Einstein's equations tell us the precise size and shape of this ring. So by measuring this feature for the galaxy M87 that's 55 million light years from Earth, the EHT team has put Einstein's theories to the most stringent test yet. And this image, the highest resolution picture ever taken from the surface of the Earth, is what we saw. It is confirmation of Einstein's theory at the edge of a supermassive black hole. It allows mathematicians, physicists, astronomers the ability to refine their models of how black holes reprocess matter and energy on galactic scales. In fact, the brightening you see at the bottom of this ring is perfectly consistent with near light speed motions of gas around the black hole. It also opens a new window on ever more precise tests of gravity. This is critical because our theory of gravity is incomplete. We have not yet been able to unify our understanding of gravity in the quantum world. To make this image, we developed specialized instrumentation that linked together existing radio facilities, enabling them to work together as an Earth-sized telescope. We reached across borders, included experts from around the globe, and leveraged billions of dollars of international resources to deliver extraordinary scientific return on investment. Support from the NSF was crucial. Before success of this project was assured, NSF funding enabled the small U.S. EHT team to grow and carry out key proof-of-concept experiments. As confidence in the project grew, we attracted additional investment from the international science community, which is why U.S. groups are in leadership positions within the larger collaboration today. The EHT collaboration now has over 200 members, representing 60 institutes working in over 20 countries and regions. It truly takes a global team to build a global telescope. And because the EHT relies on so many technical and theoretical advances, there are myriad opportunities for early career researchers to make fundamental and profound contributions. Undergraduates, graduate students, postdoctoral fellows, and junior staff have taken on leadership roles and responsibilities in areas of high-speed electronics design, innovative imaging algorithms, and modeling black holes using national supercomputer facilities. The EHT footprint across STEM fields is exceptionally broad, with rich opportunities for mentorship. Building on this success, we are working with our international partners to enhance the EHT. We aim to move beyond the still images to making real-time movies of black holes, enabling entirely new tests of gravity and extreme astrophysics. We will explore purposefully situating new dishes to fill out the global virtual telescope, and even launch radio satellites into orbit to realize an EHT that is not bound by the dimensions of the Earth. Having worked on the EHT from the earliest stages, I experienced a deep sense of fulfillment following the result. But in the end, I personally feel the greatest accomplishment was assembling an expert and committed team. The look on the faces of my colleagues when the first M87 images appeared on computer screens will never leave me. A mix of astonishment, wonder, pride, awe, and humility. Imaging a black hole for the first time has inspired our team, and we hope it has inspired you too. Thank you for the opportunity to testify today, and thank you for your commitment to keeping the U.S. a global science leader. I look forward to answering any questions you may have.
Thank you very much. Dr. Lonsdale.
Chairwoman Johnson, Ranking Member Lucas, and members of the committee. Thank you for the opportunity to talk to you about how the Event Horizon Telescope works and how its truly extraordinary capabilities allowed our team to achieve the scientific milestone we're recognizing today. A conventional telescope creates an image by focusing light from a distant object onto a sensor, much like a digital camera with a really long telephoto lens attached. Naturally, the bigger the lens, the more detail that you can see. In fact, if you can make optically perfect lenses, the magnification you can get depends only on how big they are. As Dr. Doeleman has already mentioned, since it's so far away, the black hole in the galaxy M87 appears extremely tiny on the sky. So to see it, you need a really big lens with a lot of magnification. So let's take a more careful look at just how tiny this black hole is as it appears from the Earth 55 million light years away. And I have a short video here. This is what my observatory looks like from 25 miles away. And that dome there has a large radio telescope inside it. And down at the bottom right, there's a small figure. That figure is Jason Su, who is one of our staff members who went to the South Pole actually twice to support the EHT. And as we continue zooming in, we get down to the level of individual human hairs. And if you look at an individual human hair under an electron microscope, it looks like that. And on this, to scale, that is the size of the black hole image. And just to reiterate, if we zoom all the way back out, the Event Horizon Telescope can see things much smaller than a human hair from a distance of 25 miles. So that's a fairly remarkable amount of magnification. A conventional optical telescope would need a lens several miles across to see such a small object, which is impractical. But the EHT is no conventional telescope. The Event Horizon Telescope operates with short radio waves, not light. And at radio wavelengths, our lens must be several thousand miles across, in fact, the size of the planet, to get such precision. The EHT simulates such a lens by combining signals from radio dishes thousands of miles apart using computational techniques. Imagine that these radio dishes sit directly in front of an Earth-sized lens. Radio photons come toward us from the M87 galaxy. Instead of hitting the giant imaginary lens and being focused onto a sensor, some of them are intercepted by our dishes. At each dish, we capture the photons and record them as digital data on ordinary computer disk drives. So far, so good. But to make images with our simulated lens, we need a lot of photons. The more the better. Getting enough photons to image a black hole simply has not been technically possible until quite recently. So how did we do it? First, with strong NSF support, we have greatly increased the available dish area at key sites like the ALMA array in Chile. And second, we, quote, listen for photons at many different radio frequencies simultaneously, generating more digital data. The more digital data, the more photons. So we record to 128 disk drives in parallel at each dish site. It's equivalent to simultaneously downloading 11,000 full HD movie streams from Netflix. This fills up thousands of high-capacity disks in one observing campaign, weighing several tons. Each campaign involves extensive preparation and logistical complexity. Talented and dedicated staff from different institutions travel to some of the most remote and inhospitable places on Earth, like the South Pole, driven by a common goal to create a unique window into the most extreme environments known to science. The effort level and unity of purpose is something I personally find to be truly inspiring as a tangible reaffirmation of the spirit of human curiosity that fuels basic research and the quest for knowledge. We ship the recorded disks to 2 locations, my observatory in Massachusetts and the Max Planck Institute for Radio Astronomy in Bonn, Germany, where the data streams are combined in a complex, precise, and computationally intensive process known as correlation. Our correlators simulate what a physical lens does, bringing photons that follow different paths to a common focal point, synchronized with pinpoint accuracy by atomic clocks at each observing site. After rigorous quality checks that can take several months, the correlated data are released for further analysis. Because our dishes are few and far between, we can recreate only small pieces of our imaginary planet-sized lens. Our next speaker, Dr. Bouman, will talk about how the team has used innovative new approaches to make a reliable image from incomplete data. I want to express my gratitude to the committee for the opportunity to speak to you here today, and I'd be pleased to answer any questions you may have.
Thank you very much, Dr. Bowman.
Chairwoman Johnson, Ranking Member Lucas, and members of the committee, it's an honor to be here today. I thank you for your interest in studying black holes through imaging and your support of this incredible breakthrough enabled by the National Science Foundation. My name is Katie Bouman. I'm currently a postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics, and in a few weeks will be starting as an assistant professor at the California Institute of Technology. This morning, I want to tell you more about the diverse team and imaging methods that help make the first picture of a black hole. The Event Horizon Telescope is an Earth-sized computational telescope where instruments and algorithms work together to see something that would be invisible to even the most powerful conventional telescopes of the future. Unlike a backyard telescope you may have peered through to study the night sky, the EHT doesn't capture a picture directly. It collects light at only a few locations, resulting in gaps of missing information. As an analogy, observing the black hole with the EHT is a bit like listening to a song being played on a piano with many broken keys. Since the EHT only collects sparse measurements, there are an infinite number of possible images that are perfectly consistent with the data measured. But just as you may still be able to recognize a song being played on a broken piano if there are enough functioning keys, we can design methods to intelligently fill in the EHT's missing information to reveal the underlying black hole image. To construct the image, we developed different imaging methods based on both established and newer techniques in radio astronomy. All of these methods require us to specify a preference towards certain images in order to choose among the infinite possibilities. And therefore, it was important that we carefully validate the results. To assess the reliability of imaging results obtained from M87 data, we split roughly 40 scientists from around the world into 4 teams. Each team worked in isolation, blind to the other's work, while creating an image of M87. After 7 weeks, we held a workshop where members from around the globe gathered to reveal their images to one another. Here we show the images that were revealed. Seeing these images for the first time was truly amazing and one of my life's happiest memories. This test was hugely significant. Although each picture looked slightly different, we found the same asymmetric ring structure no matter what method or person reconstructed the data. After working for months to further validate this ring shape, we combined images produced by various methods to form the image that we showed to the world on April 10th. No one algorithm or person made this image. It required the talent of a global team of scientists and years of hard work to develop not only imaging techniques, but also cutting-edge instrumentation, data processing, and theoretical simulations. There is a particular group of members I wish to celebrate today, the early career collaborators composed of graduate students, postdocs, and even undergraduates who have devoted years of work to this project. Early career scientists have been a driving force behind every aspect of the EHT. By providing opportunities for young scientists to take on leadership roles and direct significant work in the project, the EHT is training the next generation of scientists and engineers. So I personally stumbled upon the EHT project as a graduate student studying at MIT's Computer Science and Artificial Intelligence Laboratory nearly 6 years ago, and immediately fell in love. Like many big science projects, the EHT had a need for interdisciplinary expertise, and taking an image of a black hole shared striking similarities with problems I had encountered earlier in my studies, such as capturing a picture of your brain from limited data using an MRI scanner. Thus, although I had no background in astrophysics, I hoped that I could contribute from my area of expertise in advancing the EHT technology. If it wasn't for the help of a National Science Foundation graduate fellowship, which gave me the freedom to work on risky projects, I may have never had the chance to be part of this incredible endeavor. The EHT introduced me into an entirely new domain where emerging computational methods were essential to the success of scientific goals. Moving forward, the computational imaging tools that we developed to study black holes could help improve technologies of the future. My story is just one of many. I am one of the numerous early career scientists who have devoted years of their lives to making this picture a reality. However, like black holes, many early career scientists with significant contributions often go unseen. Although the EHT has been a remarkable success story, we must not forget the contributions of all these young scientists, whose names might not make it into the newspapers. For only with them and the diverse group of astronomers, physicists, mathematicians, and engineers from all around the globe have we been able to achieve something once thought impossible, taking the first image of a black hole. Thank you for the opportunity to testify and for your support of groundbreaking collaborative and interdisciplinary science.
Thank you very much. At this point, we'll begin our first round of questions, and the chair recognizes herself for 5 minutes. And this question goes to all. NSF made a significant commitment to this project without any guarantee that it would succeed. In a time with many competing financial priorities, why is it important that the federal science agencies take risks like this for basic research, even if there's no foreseeable application?
Sure. I'll start. Thank you very much for the question, Madam Chairwoman. So the definition of NSF is taking risks in science and engineering, risks that have potentially very high rewards. We saw an example of this with the first detection of gravitational waves on Earth a few years ago. And subsequently, a project that we invested in starting 40 years ago has just yielded tremendous results. Most recently, many more detections of gravitational waves in the third run of LIGO. And then just a short while ago, we announced really a solution to the enduring mystery for over 100 years of the origin of cosmic rays with the detection of neutrinos and high-energy gamma rays using our South Pole telescope and many other telescopes on Earth and in space. And so doing this kind of observation is, and the discoveries is really what NSF is about. We'd like to say that it's NSF is where discoveries and discoverers, as you heard from Dr. Bowman, begin. In my testimony, I mentioned that the GPS and in previous testimonies, MRI, companies like Google and Symantec, Qualcomm, all of these are benefits of investing in basic research. It just has, sometimes we can have benefits that happen immediately, and sometimes it takes a very long time to realize benefits. But they are, the upside is that they are truly outstanding miracles that happen when we invest in basic research.
Could I add to that, Chairwoman Johnson? I'd also add that the risks taken by the National Science Foundation for basic science are really critical. With basic science, you don't always know where you're going to go, where you're going to wind up, but by addressing the deepest mysteries in the universe, black holes, with the best technologies that we have a chance to answer the deepest fundamental questions about our universe. If you had asked Einstein, what ramifications his theory of general relativity would have had when he came up with it, he would have had no answer, right? You would have said, with our cell phones, we can now locate ourselves with pinpoint accuracy on the globe. And he would have looked at you and said, what's a phone? You wouldn't have had any idea, really, to even understand the question. That's how long it takes sometimes for the fruits of basic research to be realized. But when you ask those basic questions, they almost always pay off.
So I'd like to add something. I think that when the NSF invests in something speculative and high risk like this, and it pays off, as it has in this case, it is a real attention grabber, not just for all the scientists who are interested in doing this, but for the whole world. We heard Dr. Doeleman say that 4.5 billion people around the planet saw this. And this is the way that young people can be inspired to think about, emulating some of this work and getting involved in STEM disciplines. So it is an important component of feeding the STEM pipeline.
Yes, I agree with everything that has been said by my colleagues here. I think technology and basic science, really drive each other. They feed off each other and they help each other grow. And so it's important that we continue to invest in basic science because we don't necessarily know the ramifications of how that will manifest in technology of the future. Lots of the techniques that we've developed for imaging black holes can be adopted potentially in the future for other applications that we might not have even thought of now. And another thing is I do want to emphasize Dr. Lonsdale's point as well, and that I think that this picture has really captured the imaginations of a generation of new young scientists. And I've even had, 4-year-old girls come up to me and tell me about the black hole. And I think that getting that interest in science to young students at a young age, it will help them enter the STEM fields and make contributions to many different projects.
Thank you very much. I'm not out of questions, but I'm out of time. Mr. Baird.
Thank you, Madam Chair, and to all the witnesses. We really appreciate your testimony and the discoveries you're sharing with us today. I would also like to congratulate you, all of you, on receiving the Diamond Achievement Award this week at the National Science Foundation Awards Gala, and so I commend you for that. Dr. Bowman, I have a question that relates to the importance of the opportunity you had to do research at such a young age and had a career as a scientist. I think you conducted some imaging research at Purdue University while you were still in high school. So would you care to elaborate on that?
Sure. So I actually got a job at a lab at Purdue University when I was in the summer after 11th grade, partly because I had kind of stumbled upon a class taking a computer science class in high school, which I had never really thought about taking, but I took on a whim, and because of that, I had an interest because I understood this new language of computing, a professor there, Professor Edward Delp, invited me to help his graduate students in the lab there that summer. And that was the first time I had exposure to real research, to imaging, and the kind of the exciting world of imaging. And one thing that really grabbed me from that was being able to see the results. And I really loved being able to work on problems where you can visualize your results. And so from that, I kind of gained a love of imaging and images, and that drove me in my future, my path towards studying electrical engineering and computer science, computer vision, and eventually being on the Event Horizon Telescope project. So I think that spark of passion at a young age really brought me to where I am now. So I'm eternally grateful to my opportunities at Purdue for that.
Thank you. I guess my next question deals, maybe all of you might want to respond, but it's keeping with the theme that you had for the National Science Foundation Award. Do you have any recommendations on how we might ignite the STEMs, you know, the spark that stimulated you to get into your profession, so that we can keep these students encouraged and excited and fulfilling that pipeline to have more researchers in the future? So, Dr. Córdova, do you want to start with that?
Sure. Well, my own STEM spark was from watching a television show ages ago about neutron stars when they were first hypothesized as being responsible for certain phenomena that were being observed. And one of the MIT professors on the show talked about the energy that would be liberated if you dropped a marshmallow onto a neutron star. And I was so mesmerized by that concept. The next day, I was actually doing an education project in Cambridge, Massachusetts. I took a bus and went right down to MIT to meet that professor. And I said, this is what I want to do for the rest of my life. I want to work on this. And so for some reason, they gave me a job for the summer, and it all worked out. But so I really believe that you can have your inspiration from so many different places. And what the NSF is trying to do is fund curriculum projects that happen in schools, so computer science, you know, in the classroom, and help wonderful teachers get more skills and stuff. But we also spend part of our portfolio, as I think you know, on informal science education. So money to museums and to television shows about science. So there has to be a myriad of ways of reaching out and trying to inspire people to know more about science and be attracted to it.
It's a wonderful question, and it's one that we are really focused on in the project. I think you've seen that this image and the pins you have in front of you really resonate with the public and scientists alike. It's a real opportunity to get people at a young age, which is really when you want to ignite that spark into science. Mine came about with a stint at a museum that I worked at, actually looking over animals. So I got into this through biology, if you can possibly believe that. So you never know where the spark is going to ignite. But getting the outreach is really important for this. It's really important to get into museums, informal outreach, and also to invite the young people into labs in places where they can really do research.
I'm out of time, but the chairwoman has allowed me to go ahead and let the other two finish.
Thank you very much. Yes, well, my own spark was at a very early age also. Seems to be a bit of a consistent theme. I was looking up at the night sky when I was 5 years old and had a hunger to read all about it. My parents got me a telescope when I was like 8. And also at the same time, the US space program was taking off quite literally. And all of this was completely mesmerizing to me. And it set me on a course for life to pursue this type of work, and I see that in very tangible ways in what I'm doing now. My observatory, we have a fair amount of public outreach, and one form this takes, for example, is open houses. And just recently, I held an open house where I was, for the first time, able to talk about the black hole result, and the children in the audience were by far, they were absolutely thrilled to pieces. And I got lots of questions afterwards, but the longest time and the most questions came from a 10-year-old. And I think that connecting the scientists who have the enthusiasm for the work with the young people, you know, like 10-year-olds who have minds that are sponges for information, that is incredibly potent. And that's been my experience throughout my work in public outreach.
Yeah, so I would say, you know, throughout my early years, I had many different sparks, and I think having many opportunities to continue to grow that interest in science is so important, to have many different programs and opportunities. However, I want to highlight one that I had in 6th grade. My science teacher had us all enter the science fair. And this was the first time where I really did a science project that was outside of just your standard homework that you do. And I thought for ages about what I would work on, and I decided to work on what makes the best bread. So I actually baked probably hundreds of loaves of bread with different amounts of salt, different amounts of sugar, and different types of yeast. And I measured how big they rose and the taste. I even filled out IRB forms to have my friends taste the different bread. And that was a really fun experience, a wonderful experience. I entered it into the science fair in the area and won gold in my category. And that, I think, was my first true excitement where I knew research was a path for me.
Thank you, and I yield back.
Thank you very much, Ms. Bonamici.
Thank you very much, Chairman Johnson and Ranking Member Lucas, and thank you to all of our witnesses. I also want to congratulate the National Science Foundation and the entire team around the world for this groundbreaking work on the Event Horizon Telescope project. Congratulations. Not only was this an incredible scientific achievement, the release of the first ever image was, of course, sort of shattered the glass ceiling for women in STEM. So it was a pretty significant day, I remember, when the news hit, and it was an inspiring moment, of course, for young women who want to go work in what are still traditionally male-dominated fields in the sciences. And this certainly demonstrates the value of teamwork and collaboration in scientific discoveries. Dr. Bowman, I'm the founder and co-chair of the STEAM Caucus, where we advocate for integrating arts and design into STEM learning to spark creativity, to get more people involved, and to really have that well-rounded education that stimulates both halves of the brain. I appreciated the analogy in your testimony comparing the observations from the telescope to a song on a piano with broken keys. There's some research that shows that the Nobel laureates in the sciences are more inclined to be engaged in arts and crafts than other scientists, so it's just a little story there. So why was it important to have an interdisciplinary team to develop the imaging algorithms? And what did you learn from the development of the algorithms that could benefit future unexpected observations going forward?
Yeah, so the EHT, like many big science projects, really draws on many different areas. So, you know, at its core, it's a science project. We're trying to learn about black holes, and there we need theorists to tell us, you know, what do we expect? But also, it's an engineering project. You know, we spent over a decade building a telescope with new instrumentation that had to be put together. And because it is a computational telescope, we also had to develop algorithms and methods. And this requires us to understand computation and optimization and many different kind of how do all these pieces play together and come together to give us this kind of amazing result. So we really had to have, you know, instrumentation, algorithms, theory. It was really each part was essential. And you also have to understand each part as you know, when I started this project, actually, as I said, I came from a computer science kind of area, and I met with Dr. Doeleman, and I was like, oh, this is such an exciting project, and I kind of I decided, oh, I really want to work on it, but I kind of went off on my own and started to try to read about about the ideas of interferometry and how to make an image, and coded up some little simple algorithm. But I really, that doesn't get you anywhere just being by yourself. I didn't understand the intricacies of the data. What kind of challenges do we have with this data? And so it was really essential when it really started. When we really started being able to push the algorithms is when we all kind of got together from different parts of the team understood what kind of noise do we see in our data, what is really different about the data and challenging about the data. Even time that I spent at a telescope at over 15,000 feet above sea level, I learned where do things go wrong and how do we account for this in our algorithms. And so I think it was really essential, even on just one, making an imaging algorithm, which is just one part of this huge project, even combined information from across the project.
Wonderful. Your enthusiasm is amazing. I hope it's contagious. I want to get a question into Dr. Doeleman, who I learned is an Oregonian. And Dr. Doeleman, you told me about some of your early days with all the hands-on learning at the Oregon Museum of Science and Industry, which is a gem in the Pacific Northwest, and I know gets a lot of children and adults engaged in science. You noted that capturing an image of a black hole was presumed to be impossible just a generation ago, but now can lead to the emergence of a totally new field of science. So how can black holes be used as tests of our sort of universal theories, and what further resources are needed to succeed in the EHT's next scientific feat?
Thank you for the question. There are a lot of different ways to proceed from here. This really is the tip of the iceberg. Imagine when Galileo was looking through the first telescope, it wasn't the end of astronomy, it was the beginning of astronomy. In the same way, this image you see here is creating the ability for us to use the most intense cosmic laboratory as a way to understand the universe. Normally, you would have to build a super collider or something like that to attain the energies and the extreme physics to probe the unknown. Here, we're using the edge of a black hole that nature presents us as a natural laboratory. So in the future, we want to make movies, not just still images, because what you're seeing here is light orbiting around the black hole. That's one test of Einstein. Now we can move to matter orbiting around the black hole, make movies of this, a completely different test of Einstein, testing the period it takes for matter to orbit around. And more than that, we can see how these black holes are ferocious engines at the centers of galaxies, launching these jets that can pierce an entire galaxy and disrupt star formation. So black holes are at the heart of why the night sky looks the way it does. And as we move forward, we'd like to fill in this virtual telescope with putting new telescopes tailor-made to fill out that virtual Earth-sized array, and that will sharpen our focus and let us make movies.
Fascinating. My time has expired, but be assured we will be following the work. It's wonderful. Thank you. I yield back.
Thank you, Mr. Biggs.
Thank you, Madam Chair, and thank you, Ranking Member Lucas, and thank you to each member of the panel for being here today. I appreciate you sharing your experience and sharing with us this important discovery and how you went about it, and I think many of us are very excited to see what the next step is going to be. I would be remiss, however, if I didn't mention the contributions of the university in my home state, University of Arizona, where the sub-millimeter telescope on Mount Graham was used, and coming up for the 2020 series, there'll be the Kitt Peak Observatory will also be joining in. I'm excited about that. So having made a commercial now for my own state university, I'll now go to my questions. Dr. Doeleman and Dr. Lonsdale, when the news broke that the first image of a black hole was going to be released, many of us thought it might be Sagittarius A, the supermassive black hole at the center of the Milky Way. What have been the challenges for imaging that black hole, and do you expect to be able to produce an image of that particular black hole?
It's a wonderful question. We have two primary targets in the Event Horizon Telescope project, for both of which we can resolve that event horizon. We focused on M87 because the results started falling out very cleanly in a very pure way at the get-go. So we oriented all of the efforts of the collaboration towards that goal to get our first results out. But Sagittarius A star is next on our list. It is a little bit more difficult because during the course of one evening of observing, where we fill out the virtual lens because the Earth rotates and changes our points of view of the object during a night of observing, the source itself is changing, because it is 1,000 times smaller in mass, and therefore it's 1,000 times faster in evolution than M87. During one night of observing, M87 stays static, but Sagittarius A star evolves in front of our eyes, so to speak. Cool. So we're developing some new algorithms, courtesy of Katie and the other early career scientists, to handle that.
And I can speak a little bit to the ways that we might be able to enhance the Event Horizon Telescope. And I'm sorry, thank you very much for the question. It is right on point for some of the things that we're thinking about for the future. One of the things that Dr. Doeleman has already mentioned is adding additional telescopes to the array. And what this does is create more points in front of that giant imaginary lens to collect information. And as it turns out, if you double the number of telescopes, you actually quadruple the amount of information that's available to reconstruct the images. So because Sagittarius A star is changing quickly, we need to gather a lot of information in a shorter amount of time so that it doesn't change too much. There's a couple of ways to do that. One is to add telescopes. Another, which is perhaps a little further into the future, is to put dishes into low Earth orbit because those move much more quickly than the Earth rotates and sample more data more quickly. So we've got a couple of ways to improve the potential for imaging and making movies of Sagittarius A star.
Great, I'm looking forward to that. Dr. Bowman, what other applications can come from the computational? You had kind of touched on this, but I want to know what other applications you think might develop from computational imaging tools that were developed to study black holes.
Sure, if we're on the topic of Sagittarius A star and how it's evolving really quickly, and where you have this huge amount of evolution over the course of the night, this causes challenges from us from an imaging perspective, because the measurements that we take are taken over the course of a night, so each measurement is basically from a different snapshot of the black hole. And so we're coming up with ways of tying this information together to make not just pictures of black holes, but movies of it evolving over the course of a night. And this kind of similar, this kind of approach could be applied to many different problems. So for instance, one that has, I think, a very similar problem is in MRI, when you're studying for instance, organs that are moving, or even like fetal MRI, taking images of a baby inside of a mother's womb. And because as the MRI machine scans, the baby is moving, you actually also have to have a kind of a model of motion and understand that the picture is also evolving. So techniques that we use for imaging a black hole, similar ones could be applied to this idea of how do we image a baby inside of a mother to get a better diagnosis of issues that might happen.
Great, thank you. I still have time. I'm going to zip through this question real quick. This project is a great example of international collaboration in science. Questions are these: what makes a successful S&T International Cooperation Agreement, and how do we ensure these agreements are two-way streets, not the U.S. feeding its knowledge and talent to other countries without reciprocation? So whoever wants to take those two questions.
Yeah, I'll start. So we have a lot of international collaborations on our various facilities. A great example is the ALMA telescope that played such a big role in this observation. Also, we are contributors to the Large Hadron Collider at the CERN in Europe, and many of our biggest projects have international collaborators because the talent is worldwide, and also they help with the funding, of course. And so we have as principles for international collaboration that it has to be a win-win situation, as you said, Congressman. Everybody has to gain from this. Everybody has to contribute scientific talent and get something from it. And the collaborations have to be to do something really important that's going to move the discovery needle forward. Shep.
It's a great question. We wrestled with that, and we were successful because we adhered to some principles as we put together this collaboration. One was transparency. You have to make sure that you know what everybody is doing at all times. And we ensured that by making sure that all the working groups that we put together had members from all the different constituencies. So everybody can see actively what's going on. We didn't sequester one group here to work on one thing or one group here to work on something else. We really combined everything through the miracle or burden of video conferencing. We tend to live our lives on video cons these days. But it's really true that you can publish with someone now that you've never met. And it's kind of an uplifting way to think about things, right? I mean, we can really broaden the team across borders and across cultures and across different practices in this way. And we also had very strong policies on publication and how to proceed with allocation of resources and planning for the next arrays and how we're going to go to the next generation. So by being very inclusive, we got the best of everyone, and we also made sure that everyone saw what we were doing. And that is one of the principles that I think has made us successful.
Thank you very much. Mr. Lamb.
Thank you, Madam Chairwoman. This is a question for anyone that's knowledgeable about it, but I was curious about the supply chain for the construction of the telescopes themselves, both the current ones that we have and the additional ones that may be coming. Are we relying on a lot of American businesses and American materials for these things? And I would ask the same thing about the software and computers that we're using for the imaging as well. So if anyone is able to address that, thank you.
This particular project was completely reliant on telescopes that already existed all over the world, obviously on many continents. And so their supply chains are all different. In the case of U.S. telescopes, of course, we try to do our best to use American-made products. We have a few telescopes that were used, right, in Arizona, in this country, and Hawaii, and we anticipate more of those. But this is really all about a global supply chain.
Thank you for the question. I would add that while we all work together, all of the constituencies within the project realize that they want to use local resources where possible, so we lever that. So Europe uses the best construction practices and companies in Europe, but we use the best construction practices and companies here in the United States. We define what the instrumentation has to do, and then we apportion who's going to do what based on the local resources. So we've been very careful to lever U.S. businesses when we can. And I just want to give a shout out to Arizona again that the submillimeter telescope on Mount Graham was involved in the very first observations that we ever made of Sagittarius A star that got this whole thing started. And it was the investment of the NSF in that U.S. site that really made that possible.
Thank you. Are there particular companies in the American telescopes that have been leaders or been especially reliable for us in the construction of these things, or that we might be looking to going forward?
Do you want to?
You may have particular examples, but we can certainly, Congressman, get together a list of that and give it to you. There are many and complex. I do know that at our own universities, there are amazing work is going on by investigators that we fund to build a lot of telescope optics, and so that's a great credit to the way the science engine works.
Actually, if I may, a very interesting tie-in here is that the size of the telescope you need depends on the bandwidth, as Dr. Lonsdale was describing. So by investing in high-speed electronics, for which we use like Xilinx, for example, which is a U.S. company, to do the throughput on our field programmable gate arrays to get a little bit wonky, that decreases our reliance on steel necessarily. So we don't need to build huge telescopes. We can collect more data by recording bigger slices of the radio spectrum and make the dishes smaller. That changes the kind of company you go to or the kind of designs you do. So it's very interrelated. And it's a very interesting optimization problem. And that's what we're working on now.
Thank you. Madam Chairwoman, I yield back.
Thank you very much. Oh. I'm sorry, Ms. Gonzalez.
Thank you, Madam Chair, for holding this hearing and for all of us that are here today. I think this is a remarkable event and achievement. I want to congratulate everybody involved in this. Dr. Doeleman, from what I understand and reading your statement, the project is looking to expand by including 3 new additional telescopes. Do we have identify where those telescopes are going to be included from? Any country that you're working right now on that regard that you can share with us?
Sure. We're looking broadly at how to fill in this Earth-sized virtual lens. So in the next year, we'll be including a new telescope in France, NOEMA, which is an array that's in the French Alps, and that's already very underway. The Kitt Peak telescope that the Congressman mentioned will be lighting up on the Kitt Peak National Observatory. That's another one. Beyond that, we're looking primarily at potential new sites where we'd like to put new telescopes. And for that, we're doing some optimization studies now. In fact, we're putting a proposal in soon for that, which will lead to a global design for where we want to put the next site. So it's very interesting when you look at this image and you say, well, how can we make it better? There are metrics, right? You can say, well, it can be sharper, it can be more sensitive. And so where you put the telescopes affect those metrics. They affect how much better the image would look. And you can make what we call a heat map. You can look on the whole globe and find out where you need to put the next telescope to maximize the scientific return from this image. And so we're looking at that now, trying to find out where we want to put them. And then we think we can put modest dishes, smaller dishes, at these new locations to build out the full array.
So that's the process to select those telescopes and the places they're going to be installed.
That's what we'd like to do, yes.
Okay, and what are going to be the main challenges for you in that process of selecting which telescopes and where those telescopes are going to be installed?
Well, what's that? Yeah, getting funding. I'm told by Director Córdova that getting funding is very
clever.
And it is. But the first part is design, really. It's coming up with the new algorithms, the new metrics, the stuff that Dr. Bowman was talking about, and the new electronics that Dr. Lonsdale was talking about, folding that all into the equation, finding out where we can get the best value for the taxpayer's dollar. Like, where can we target the locations of our next dishes to ensure that for the best return on investment, that we can get that.
The increase in cost, of course, by installing those new telescopes will mean that you need to plan ahead. Are we willing to look in the private sector investment to help out in this endeavor?
Well, it's a wonderful question. So it turns out that when you get a result like this, others want to invest in it too. So we currently have an NSF award for which Google is partnering with us to help us move some of the computation that we do, because it is very computational intensive, as Dr. Bowman said, to the cloud, where we have virtually unlimited processing power, for example. Same thing with some of the high-speed digital electronics. So we're working definitely in that direction.
Right. Dr. Bowman, I read in your statement as well that you mentioned that given the limited number of telescopes and limited number of locations, there are information gaps. From what I understand, the project is looking, of course, to increase the cooperation of those other countries. The doctor just explained the process for the new challenges. Can you tell us about what were we expecting to see in those new using those new telescopes?
So we aren't just observing M87 once. It's not like we observed it and then we go away and we look at other things. We're going to continue to every year go back, improve our instrument, and try to learn more and more. So, and look at other sources like Sagittarius A star. So when we are simultaneously improving the instrument and our algorithms to work together to answer these questions. And I think that now that we have a first image and see that it is possible to see this ring, then we can go back and say, okay, where are our missing information? And we can target those areas through new instrumentation and algorithms and try to answer those questions and get a clearer picture of GR and light, general relativity, and how it acts around a black hole. So I think that is something that we look forward in the future to seeing.
Thank you, Doctor, and thank you, Madam Chair. I know my time is expired, but I know that the broader implications of this discovery will help a lot of areas between physics and data science. I yield back.
Thank you very much. Mr. Caston.
Thank you, Madam Chair. Thank you to all the panelists. I got to tell you, you guys should take the show on the road. Your enthusiasm is just so infectious, and it's so cool. So I learned a valuable lesson, I hope not to repeat, last week, which is that if you miss an episode of Game of Thrones, you find out a couple days later that apparently it all ends with dragons. I don't want to do that again, so can you give us a little hint of what you mentioned that you're going to be able to now tune this on the black hole at the center of the Milky Way. When should we be tuning in for that?
Okay, well, as they say, I would tell you, but. So first of all, let me say that bound by a common science vision, it really helps when you want to prevent a leak. So what really surprised people with this result was that people thought it was going to be on Star. And we had 200 people from around the globe, and nobody broke the code, right? Nobody broke the silence. And I think it's because we all understood the impact that it would have, and we wanted to be able to tell our story, the scientific story, after peer-reviewed publication of our results. So that was a key part of it. And as we go forward and look to Star, for which we'll be using new algorithms and new computational platforms, we're going to be attacking that with the same rigor and the same cross-checking, the same purposeful tension within the collaboration that allowed us to produce this result. So we'll be splitting up into teams probably, as Dr. Bouman described. We'll be cross-checking, double-checking, making sure that one frequency gives us the same image as a different frequency, one polarization gives us the same image as the other polarization. We'll check everything, and only after that will we reveal in an episode of Game of Thrones.
Well, no. I will take that as a constructive non-response, and I will not pressure.
I would estimate within a year.
Well, a part of why I'm intrigued is that you've talked about that there's sort of tests of Einstein's relativity in this, that you'll be able to do other questions, and then this whole idea of like actually seeing a movie of this. And I guess I'd just love to hear your thoughts about what are the types of questions that we can answer once you tune it there, both in terms of looking at the Milky Way and in terms of potentially getting some movement. What types of questions are you going to be able to learn at that point that we don't know now?
Well, the black hole at the center of our galaxy, Sagittarius A star, may look different from what you see on the screen there in a few different ways. The black hole at the center of the Milky Way is in a different environment. It's accreting material at a very low rate. It may be oriented on the sky in a different way. And so there's a lot to learn by looking at different black holes. We don't know what we'll find. It's one of those things where it's right at the frontier of what we're technically able to do. So it places a tremendous emphasis on checking and double checking, as Dr. Doeleman said, to make absolutely sure that we know not only what the image is, but what the uncertainties on the image are. So we're going to be working hard on that.
So if I understand, you've got a couple more telescopes that you're adding. You've got one that you added in 2018, and then two more in 2020. If I've got that right.
Yes.
Well, we're adding two more next year for the observing campaign in 2020, and then we're looking to the future to add even more than that.
Okay. So what sorts of things are you going to be able to see once you have those additional data inputs? And I'd love to know from Dr. Bowman, like, as you think about sort of analytically, what holes in your data field, if you will, are going to be filled in with those additional, what are you sort of salivating to see once you get those additional points?
Yeah, so I think, one thing is we don't know what we're going to see, so that I think is part of the mystery and excitement of it all. But one thing is if we zoom in towards Sagittarius star, all this variability that hopefully by adding new telescopes we'll get a better grasp of, we can better map out the space-time around a black hole. So right now, we just have a static picture, but just like seeing a movie tells you so much more about your environment than just a single picture. Getting that movie will allow us to learn so much more about the black hole. For instance, the black hole in M87, we get an estimate of its mass, the size it is. But by seeing this evolution around a black hole, maybe we can learn about not just its mass, but its spin. And knowing both the mass and the spin tells us about how it should affect the space-time around it. And so I think that being able to have a grasp on that will teach us a lot.
Well, this is very cool. I yield back. Thank you.
Thank you. Dr. Babin.
Yes, ma'am. Thank you, Madam Chair. And thank you all for being here. Dr. Córdova, I enjoyed you accompanying our committee. I guess it's been a year before last when we went to the Arctic and saw some neat things. Good to see you again. I wanted to ask a question about return on investment, and I'd like to hear it from maybe all of you, if you get a chance. We'll start with Dr. Córdova. Our constituents may ask, why invest taxpayer funding in imaging a black hole? And that is, what can you tell them, or what can we tell them, has been the return on their investment? And I liked what is it Bowman or Bowman?
I don't mind either, but Bauman
Okay,
is what I usually say.
all right. Bowman said, we don't know what we don't know. So that's kind of a mysterious thing to say, but we've got, if we can ever get James Webb Space Telescope up there, I assume that's going to open up some new windows and horizons for us as well. But let's start with you, Dr. Córdova, on return on investment, where somebody says, what are we getting for spending all this money on imaging a black hole?
Well, there's three ways I like to answer that, but I want to give a lot of time to my colleagues here. So I'll just say the three words are inspiration, and that is that's at the root of who we are as human beings, and that's what draws us into our fields where our passion and our commitment is. And we all were sharing earlier our STEM spark, and so it's so important with young people to get them inspired. So we had great moments like landing on the moon and discovery of the Higgs boson and this imaging of the black hole, and who knows how many people that will attract into science, all kinds of science and engineering. The second one has to do with all the engineering and computational tools that go into a discovery like this, a challenge like this. It took them over a decade to do this, and as you know, with the LIGO gravitational wave experiment, it took 40 years to do that one. And the amazing amount of engineering prowess and computational prowess that it takes in order to make those kinds of feeds have many, many spin-offs. There are many things that are invented for the first time that then go off into spin-offs. And the third one is that when we invest in truly fundamental basic research, it can have enormous benefits, not just little incremental benefits, but we talked earlier about GPS, about MRI technology, about new companies that are invented like Google itself. These start at the root with just a little piece of fundamental research, and even the people who are discovering it. We funded Charlie Towns, the Nobel Prize winner. We gave him 17 grants over his lifetime, and he never said, I thought it would end up in the maser, and we used masers here in this as the clocks in order to synchronize the telescopes. I never thought it would end up in the laser, but and doing eye surgery and all. But he did it because he was driven towards a fundamental discovery, right. And so these have amazing benefits for the public, but sometimes a little later on.
The quest for knowledge and curiosity. That's
yes.
Right. Doctor, is it Doeleman? Doeleman, yes, sir.
Although I answer to many things. So when I talk to the team about what we're doing, I often use the analogy that we're jumping off cliffs and inventing parachutes on the way down. And that's really emblematic of this project. We're asking and hoping to answer the deepest questions, and you don't know where they're going to lead.
Right.
If you limit yourself by attacking questions that you can see what the return might be, then you're really limiting where you're going intellectually and where we're going as humans. It's by asking these open-ended questions that they inspire, as Dr. Córdova said, but also that you get these amazing discoveries and the ancillary benefits.
Right.
Any normal portfolio advisor will tell you want some stocks, you want some bonds, but you also want some high-risk, high-return in there somewhere, just on the off chance you're going to invest in Amazon or something like that. And sometimes it pays off, as it did here, and it really does inspire people. So if you want to make the discoveries and have the benefit, you've got to take a little bit of risk.
Absolutely. And Dr. Lonsdale, we're running out of time. So.
Yes, thank you. I'll try and be brief. For me, I already mentioned the inspiration aspect for young people and getting people into STEM. I'd also like to very briefly mention that at my observatory we have an interdisciplinary research program, and the techniques and technologies that went into the EHT echo throughout all of the research that goes at the observatory, and I think that that's true on a broader front as well. So we do geospace science, for example, and it's benefited from some of the work that's gone on in the EHT.
Right, thank you. And can we indulge Dr. Bowman for just a second?
Sure. So I think I want to just echo everything that my colleagues have said here. I think the technology and basic science really drive each other to be better. And things that we develop for imaging a black hole, we don't necessarily know how what they'll manifest in technology of the future, but I think that they definitely will. I'm very confident of that, and I also think that just capturing the imagination of young students and getting them excited about science and STEM, I think that in itself will lead to a lot of innovation in the future.
All inspirational answers. Thank you very much, and I yield back.
Thank you very much. Ms. Horn.
Thank you, Madam Chairwoman, and thank you to all four of you. What an exciting and important conversation and inspiration that this discovery is. I think, Dr. Córdova, the inspirational factor, I think, can't be undervalued, and the discoveries that come after that. And Dr. Bowman, I want to turn to you first because we recently had a hearing on diversifying STEM fields with some really fantastic witnesses as well. And I think you are a prime example of what that looks like and how a diverse pool of scientists is important and can bring different things. So my first question really, as we inspire or work to inspire a future generation, is what inspired you to pursue this field of study?
Yeah, so I think, I didn't ever expect to come into this and work on this to be a figure of diversity. I was just excited by the science, excited by the mystery of what we were working on and what we could achieve together as a team. And I think that highlighting just not my story, but the stories of many different scientists in the collaboration who come from many different backgrounds, who have many different experiences, I think is wonderful. And I think that as we've been talking about young students and getting them excited, it's important to show the diversity of people that was necessary to make it possible to get this picture, because we required that we had many different people that kind of came to it with different ideas of what should we do, and we kind of whittled it down to the best of the ideas, and I think that was really essential.
Thank you. I think that's an incredibly good point, is it's not diversity just for the sake of diversity, but creative new ideas and perspectives that people from different backgrounds, different experiences can bring to the table. So following along those lines, I'd like to know a little bit more about your early research and the contributions and how you see that as helping to shape your next step as you move into becoming a professor. So.
Yeah, so I've learned a lot through the Event Horizon Telescope project. One thing that it provided, the Event Horizon Telescope project provided, is many different opportunities for leadership. And there were many opportunities in many different parts of the project were kind of guided by people such as myself, early career scientists, and kind of we led the direction of different parts of the project and had to come up with creative solutions to problems that kept popping up everywhere. And I think by doing this and having to lead teams of tens to hundreds of people in this and kind of converging on one story and one kind of result was really helpful for me in my next stages of my career, where hopefully I will be leading a group of students there, and I think that the skills that I learned as part of the EHT will be invaluable for that, and something that I think is rare to have at a young age. And so I think that the EHT is doing a wonderful job at providing that opportunity for young scientists.
Thank you very much, Dr. Bowman. I agree with you. It's easier to envision yourself as something that you can see, and I think there are a lot of ways that we can do that. I want to turn to Dr. Doeleman for just a moment in the little over a minute we have remaining, and I want to ask Dr. Doeleman what should be done to help you in recruiting and maintaining postdocs and other students to help continue to grow the pipeline of scientists and researchers?
Thank you for the question. I just want to amplify something that Dr. Bowman said, that there is no EHT 101 course taught in astronomy curricula. Doing something new, so fundamentally fresh like this, requires that we draw upon the best from many, many different fields. So I think the thing to do is to invest in some interdisciplinary positions, perhaps postdocs and graduate student positions. At Harvard, for example, we've started the Black Hole Initiative, which brings together mathematicians, physicists, astronomers, and also philosophers and historians of science, all of whom see the black hole as an anchor point in their respective fields. And in that crucible of interdisciplinary kind of mishmash of wonder, we were now graduating our first students who have exposure to all of these different fields together. And that is really something that I think lifts up the EHT and provides an example for the kinds of students and early career people that we need.
Thank you very much. My time has expired. I just want to say thank you to all of you for the work you're doing, and it's really great to have you here. I yield back.
Thank you very much, Mr. Posey.
Thank you, Madam Chair, for holding this hearing, and thank all of the witnesses for appearing before what is clearly the most interesting and the most exciting committee in Congress. I so enjoy it, and you just bring yet one more incredible dimension to the things that we get to explore with you. Dr. Córdova and Dr. Doeleman, given your statements that the capture of the first ever image of a black hole by the EHT would not have been possible without American leadership, I just wondered if either one of you could elaborate just a little bit on some examples of what you mean by that.
Well, in this case, what I really mean is that we were in it for the long haul. And that's true with most of the projects that we take of this nature that are, and we've been funding this project for about 20 years or so, over a decade. And we funded the LIGO gravitational wave project for 40 years. And we consistently fund high risk but potentially high reward projects. So that was just essential in this case.
Okay. Dr. Doeleman?
Yeah, if I could expand on that, and springboarding off of what Dr. Córdova said, this project started some time ago, and it was quite risky at the first stages. We really didn't know if there was even anything that small towards M87 or the galactic center Sagittarius star that Dr. Bowman talked about. And it was some early proof of concept experiments using cutting-edge instrumentation by primarily U.S. groups that set the stage for the eventual build-out of the EHT. And so when we talk about leadership, it grew from a history of taking risks and being at the forefront at the very outset of the project. And then as it became clear that the project could succeed, then we began to attract more international investments and investments even from within the U.S. So it grew, but always with a nucleus of some U.S. expertise at its core.
Well, if somebody had told me we're going to locate and coordinate these various telescopes around the globe, and we're going to coordinate them so that you could read the date on a dime from New York with the dime being in Los Angeles, I'd think that's insane. So, a lot for your courage and your faith in what could be accomplished. Dr. Lonsdale, anything you'd like to comment?
Well, certainly the accomplishment is something to be very proud of. I look at the scale that we're able to magnify this thing to, and it still blows my mind now, even though I was deeply involved in it right from the beginning. As Dr. Doeleman said, the National Science Foundation has been supporting this work. Actually, I think the foundations of this go even before 20 years ago, when we started working on 3mm VLBI in the mid-90s. So the foundations for this have been going on for a long time, and it was really quite visionary on the part of the National Science Foundation, in my opinion, to have sustained investment in this, and it became apparent as Dr. Doeleman said that the event horizon scale structure could be accessed. I have to admit, I was skeptical initially. Dr. Doeleman convinced me after a bit of time. But it's been a wonderful experience and a wonderful ride.
Dr. Allen?
Yeah, I think one thing that has made this so strong is that we do have, to make a global telescope, we have a global team. But it has been, from many students, from students to, senior scientists from the United States have really pushed this project forward from the beginning. And I, as a younger person, see this in my mentors, but I think that it's wonderful at how they've kind of had the courage to stick with this for the last, 20 years to achieve what we have today. So I think it's wonderful.
But, I don't think the accomplishment could be overstated, and I just hope the public learns more about it and would have to become excited about it and more about science, and especially our young people. Thank you, Madam Chair. I see my time is up. I yield back.
Oh, can I add one last thing? Would you mind? Yeah. One thing that I think needs to be said is that the U.S. attracts the best and the brightest, really. We have some of the best research universities in the world. And when we get a result like this, we get a lot of interest from around the world, from postdocs, from graduate students, from early career researchers who want to come and join the team here in the U.S. So this is really a recruitment moment, not just for early career or early STEM people, but it's a way for us to get the best people here. And some of them go back, some of them stay here, but they all infuse the project with their intellect.
Thank you. Thank you for sharing. Thank you, Madam Chair.
Thank you. Mr. Byer.
Thank you, Madam Chair, and thank you guys for coming back again. It was, I've had a chance to be here on a flyout day when you presented a couple of weeks ago, and it was very much fun to see it, but I was also incredibly impressed with the quality of the questions asked by our staff. And I was impressed to find out that we now have 4 astronomers and 2 physicists just on the Democratic side. And of those 6, 4 of them are women, which is another thing to celebrate. So it's great to have you back. Dr. Doeleman, you talked about how you might be able to make a movie of the black hole. How will that be different from Matthew McConaughey flying into the black hole in Interstellar? Is that what you're envisioning? Or
Well, we're hoping to bring him onto our team.
Okay. Put Ed Perlmutter on the team, too, though, please. We'd love to have him.
But it's a great question. The human intellectual palate gets sophisticated pretty quickly. So it wasn't 5 minutes after we released this image that people were saying, well, what's next? And we were too, quite frankly. I think we were all asking what's next. But by making movies, we access a completely different realm, as Dr. Bouman was saying. We can add some new telescopes around the globe to sharpen and fill out the virtual lens. And by seeing the motions of matter orbiting around, which can't, of course, move at the speed of light, we test Einstein in a completely different way. And for Sagittarius star, where this is very important, it's a completely different kind of object. Keep in mind that it's 1,000 times smaller in mass than M87 here. So it's a completely different kind of object from an astronomical point of view. It's much more similar to all the black holes in most of the galaxies in the universe. Yeah. So by being able to study Sagittarius star, we can study most of the universe.
You set up my next set of questions, because I was very much intrigued that you guys hadn't been smart enough to come up with a theory of quantum gravity yet. So I've been asking a lot of people about it since and reading up on it. And I've long been a fan of string theory because the math works, right? But in string theory, you have 26 dimensions. No, boson string theory, superstring theory, 10 dimensions. How does this work on imaging a black hole help you think about quantum gravity?
Yeah, so it's a really good question. So on the scale of the event horizon, we tend to think of black holes as classical objects. In other words, the quantum realm doesn't really take hold until you get to the singularity that's shrouded by the event horizon. When you get to that singularity, the density is so high and the force of gravity is so strong that finally gravity gets to play with the big forces, like the strong force and the weak force that control things at the nucleon level. And only there does that happen. That's where you need to unify gravity and the quantum world. At the event horizon, we don't think there's going to be much effect from quantum gravity there, but there could be. In other words, there are some theories where you get manifestations of the quantum world on horizon scales. And people have done some simulations now of what that might look like.
When you get to the singularity, will you be able to think about things like quantum entanglement?
It's possible. I'm not sure. I'll be honest with you. I'm not sure how the Event Horizon Telescope is going to see through the event horizon. We haven't quite got there yet. But if the quantum fluctuations can be manifest outside the event horizon, then looking at the electromagnetic radiation from the black hole boundary, as the EHT does, could give us a window into that.
So all of us here are big fans of James Webb. We're all big fans of WFIRST. Will this work also give you insight into dark energy and dark matter? Or is it?
Well, it is possible to think about dark matter and dark energy from this perspective. So, for example, there are theories that dark matter consists of black holes and things like that. And there are also some possibilities that axion particles, which could be constituents of dark matter, dark energy, could be resolved or studied with the Event Horizon Telescope. But that kind of remains to be seen. That would have to be through a next generation version of it.
And could I
yes, Dr.
just
Córdova.
add that NSF has some other telescopes coming online, like the Large Spectroscopic Survey Telescope, LSST, in Chile, that is going to really address dark matter and dark energy.
Great, thank you. And Dr. Bowman, it was fun to read in Dr. Córdova's statement about the 1,000 hard disks and the too much data to go over the internet and 3 tons. And so you're a computer scientist. What's coming in terms of data management to be able to deal with these huge amounts of data?
Yeah, well, luckily, from an imaging point of view, by the time we start making the images, this data has already been whittled down to a much smaller amount of data. And then our problem is we have too little data. But actually, there are groups of people who take the 5 petabytes of data that we collected and get it down to megabytes. So basically, they try to find this weak signal riding on a huge amount of noise, and process it down and calibrate it so that we kind of can make these measurements that we then use to make images. But even then, this has required huge amounts of computational power to make these 5 petabytes down to the megabyte level. I think Dr. Lonsdale will have a lot to say along that line.
Yeah, well, just briefly, one of the biggest challenges that we face is actually taking the data from the telescopes where it's recorded and physically moving it to one place so we can combine it. And that's a particular problem for the observations taken at the South Pole. Of course, these observations happen in the northern spring, which is when winter is closing in Antarctica. So we can't even get the data physically for months and months and months. And ways to ameliorate that problem are under study, including the possibility of laser-based communications via space relay, which has the potential for enormous data rates that would allow us to get the data much quicker and do the whole process more efficiently.
Great. Oh, thank you very much. Madam Chair, I yield back.
Thank you very much, Mr. Perlmutter.
This is an incredible panel. I just thank you. The enthusiasm, as Mr. Kasten said, it really is infectious. So many, many years ago, I wrote my term paper in astronomy on black holes.